everyone. This is Dr. Aruna working as Associate Professor in Department of Chemistry, Aditya University. Let us start with nano and smart materials. First of all, let us discuss the prerequisites of nanomaterials. The study or work with nanomaterials, a foundational understanding of several scientific areas is crucial. These include basic chemistry, physics, and material science with a focus on topics like thermodynamics, atomic structure, and crystallography. Additionally, knowledge of synthesis and characterization techniques for nanomaterials as well as their unique properties is essential. Let us try to know the prerequisites of another material which is known as smart materials. Smart materials are characterized by their ability to sense the changes in their environment and respond to them in a predictable way. This responsiveness requires several key prerequisites, including stimuli responsiveness. Smart materials must be able to detect changes in their surroundings, such as temperature, pressure, pH, light, magnetic field, or electrical fields. Now, let us start with what is a nanomaterial. Nanomaterials are materials with at least one dimension in the nanometer range, which is of 1 to 100 nanometers, are revolutionizing engineering due to their unique properties. As we know that nanomaterials are materials which come in the range of 1 to 100 nanometers. These small materials are the small size particles, exactly saying the small size particles are brought a revolution in engineering due to their unique properties. These properties include such as enhanced strength, conductivity, and reactivity stem from the increased surface area to volume ratio and quantum effects at the nanoscale. Nanomaterials are finding applications across various engineering fields, including electronics, medicine, energy, and material science. Let us try to understand what are the key concepts of nanomaterials. One is size dependence. Nanomaterials exhibit unique properties that differ significantly from their bulk counterparts due to quantum confinement and increased surface area. So we see that why these nanomaterials are gaining significance. The reason behind is due to their unique properties. Why they have unique properties? We see that they are due to their quantum confinement, due to the small size particles. These small particles will have increased surface area. Due to the increase in surface area, we see that they are having unique properties. And other one is synthesis methods. Nanomaterials can be synthesized using both top-down, example, etching, lithography, and bottom-up, which include self-assembled chemical vapor deposition approaches. And the next concept is about the classification. Nanomaterials can be classified based on their dimensionality. So we do have nanomaterials which are of zero dimension nanoparticles, and we have one dimension nanotubes, two dimension films, three dimension bulk materials, and they have composition and structure. So we see that nanomaterials have been classified based on their dimensionability, composition, and structure. These are the broad or wide classification given for nanomaterials. Let us see some examples of nanomaterials. These examples of nanomaterials include carbon nanotube. So we see that carbon nanotube is a strong material which is light in weight and electrically conductive, and this carbon nanotube is being used in aerospace, electronics, and sports equipment. And other example for nanomaterial is quantum dot. So this quantum dot has been used in semiconducting nanocrystals. We see that these quantum dots in semiconducting crystals are found with tunable optical properties, especially which are used in displays, solar cells, and medical imaging. And we see that other nanomaterial is a fullerene. A fullerene is a spherical carbon molecule which is having the shape of a buckyball, that is a football. And this fullerene is having unique electronic and mechanical properties which are being used in drug delivery and material science. And another nanomaterial is graphene, a single layer sheet of carbon atoms with exceptional strength and conductivity used in electronics, sensors, and composite materials. So we see that these are the examples: carbon nanotube, quantum dot, fullerene, graphene, all these come under the examples of nanomaterials. And here we can see that each nanomaterial is having unique properties, and we see that they are having a wide range of applications, especially in aerospace, in electronics, in medical imaging, in solar cells, in material science, in drug delivery, in making composite materials. So these are in making of sensors. So these are some of the examples of nanomaterials which are having unique properties and which are having a wide range of applications. And let us see how these nanomaterials have been used in the field of engineering. So in engineering applications, nanomaterials have been used in electronics. Nanomaterials are used in transistors, sensors, and interconnects, enabling smaller, faster, and more energy efficient devices. They are also used in medicine. Nanomaterials are used for drug delivery, diagnostics, and tissue engineering. Nanomaterials are also used in energy. Energies such as solar cells, batteries, fuel cells, and catalysts, improving energy efficiency and storage. Nanomaterials have been used as material science. Nanomaterials are used to enhance the strength, durability, and functionality of various materials such as coatings, polymers, and composites. So we can see that these are few applications where they are used in electronics, medicines, energy, material science. Now let us discuss what are the challenges and future directions. So the challenge lies in its synthesis and scalability. Developing cost effective and scalable methods for producing nanomaterials is crucial for widespread adoption. So we see that the synthesis is cost effective and scalable methods for producing nanomaterial is crucial for widespread adoption. So we see that the synthesis and its scalability are not so easy as they are cost effective and it is very difficult to scale them. And another challenge is in characterization and control. Accurate characterization and control of nanomaterial properties are essential for reliable performance. So we see that the characterization should be very accurate for these nanomaterials, and because the size of the particle is very important, and the properties depend on the size of the nanomaterial. So that is also one another challenge. And the other one is in environmental and health concerns. Addressing potential environmental and health impacts of nanomaterial is a priority. So we see that this nanomaterials is having some environmental and health impact. So that is also we need to address. So these are the challenges and future directions. Now let us start with what is a nanomaterial. Nanomaterials can be metals, ceramics, polymeric materials, or composite materials. So once again I repeat, nano means which are very small size particles. But these particles can be made using a metal, ceramics, polymer materials, or composite material. Nanoparticles are particles within the size ranging from 1 to 50 nanometers, and nanomaterials having components less than 100 nanometers at least in one dimension. So here we have to clearly understand the difference between nanoparticle and nanomaterial. Nanoparticle means that the size of the particles are in between 1 to 50 nanometers. We call it as a nanoparticle. And if a material in any one dimension, if it is having size which is less than 100 nanometers, then we can also call the material as nanomaterial. Now let us discuss about the classification of nanomaterial. So here, coming to the classification, we have the zero dimension nanostructures such as metallic, semiconducting, and ceramic nanoparticles. So all the metal, semiconductors, and ceramic nanoparticles are having zero dimension. One dimension structures, for example, we do have the nanowires, nanotubes, and nanorods, which are having one dimension nanostructures, and two dimension nanostructures, which include graphene, nanofilms, nanolayers, nanocoatings. So these are the materials which are having two dimension, and three dimension nanomaterials such as bulk powders, the dispersions of nanoparticles, bundles of nanowires, nanotubes, as well as multi-nano layers like diamond and graphite. All these come under three-dimension nanomaterials. So now I think we can see that nanomaterials have been classified into zero dimension, one dimension, two dimension, and three dimension nanomaterial. So here we have a very clear picture showing the zero dimension, one dimension, two dimension, three dimension. Zero dimension nanomaterials have dimensions, all dimensions at the nanoscale. So we can call a material as a nanomaterial with zero dimension when all its dimensions are at the zero dimension. Two dimensions at the nanoscale, one dimension at the macro scale. We call such materials as one dimension nanomaterials. And two dimension nanomaterials are those which are having one dimension at the nanoscale and two dimensions at the macro scale. And three dimension materials are which are having no dimensions at the nanoscale, all dimensions at the macro scale. So in this way, we have nanomaterials classified into zero dimension, one dimension, two dimension, and three dimension materials. Now, let us discuss how these nanomaterials are synthesized. Coming to the synthesis of nanomaterials, we have two methods. One is top-down and the other one is bottom-up approach. There are plenty of methods to synthesize nanomaterials. So these methods are grouped into two categories, namely top-down and bottom-up techniques. So even though we have several methods of synthesizing nanomaterials, we have categorized synthesis of nanomaterials into two categories. One is top-down approach and the other one is bottom-up. In the top-down class of techniques, the starting material is in solid state. So here we have to remember that whenever we need to prepare a solid state nanomaterial, we have to go for the top-down technique. Or we can simply say that top-down technique is designed for the starting material which is in solid state. Whereas in bottom-up technique, the starting material is either in gaseous state or in liquid. So if our starting material, nanomaterial, is in gaseous state, or if you want to prepare a nanomaterial in a gaseous state or in liquid state, so if the starting materials are in both the state, then we go for the bottom-up techniques. So here we can clearly see that what is the physical state of the nanomaterial that we want to prepare. Based on that, we do have two techniques. One is the top-down technique and the other one is bottom-up technique. So in top-down technique, if we want the nanomaterial in solid state, we go for the top-down technique. If you want the nanomaterial in gaseous state or in liquid state, we go for bottom-up technique. The top-down breakdowns big molecules into tiny nano-sized particles. So here we see that the technique, why we are calling it as top-down technique, because we see that in this method, the big materials are made into small size, that is nano size piece, while the bottom is builds up nano size structures from small atoms or molecules. So bottom up technique, we bring small molecules together like the atoms or molecule to form the nanostructure. So in this way, based on what is the physical state which the nanomaterial has to be prepared, we do select the techniques. And these techniques are entirely different, where the top down technique, we have big material coming into nano size, and in bottom up technique, we bring small molecules into big nano size material. So here we have the techniques which have been used in top down and bottom up technique. So in top down technique, we do have the mechanical grinding, that is ball milling method, and lithographic technique, etching technique, erosion technique. So top down technique is again divided into four types. We have mechanical grinding and lithography, etching, and error. And coming to the other side, we do have the bottom up techniques, which include the sol gel method, chemical vapor deposition method, physical vapor deposition method, electrochemical deposition method, hydrothermal method, and atomic layer deposition. So we see that in bottom up technique there are around six techniques like the sol gel method, chemical vapor deposition technique, physical vapor deposition technique, electrochemical deposition, hydrothermal method, and atomic layer deposition. So now I think we could understand what is a top down and bottom up. So, based on the physical state of the nanomaterial that we want to synthesize, we do select the top down and bottom up. And this top down is again having four different techniques. So, based on our convenience, based on the method, we can go for these four techniques in top down. And based on the final end material that we want to synthesize, in bottom up technique also we do have six different methods, so we can choose any of these methods in preparing the nanomaterials. So finally I would like to end this module where students will be able to understand what is a nanomaterial and what is the classification given for nanomaterials, and the synthesis of nanomaterials and their applications in engineering. Thank you.